Welcome to this comprehensive tutorial on Pytorch Dropout. Today we're going to explore one of the most powerful regularization techniques in deep learning, Dropout, which helps prevent overfitting by randomly deactivating neurons during training. We'll start by understanding how Dropout works, then master its parameters and behavior through hands-on examples. By the end of this tutorial, you'll know how to identify and avoid common pitfalls when using Dropout and apply it effectively in your neural networks. Let's begin by looking at the fundamental concept of Dropout as a regularization technique that randomly drops neurons to improve model generalization. Here we have a visual representation of the Dropout architecture. This image shows how Dropout works in a neural network. During training, Dropout randomly selects neurons and temporarily removes them from the network along with all their incoming and outgoing connections. This creates a different subnetwork for each training batch, which helps the model become more robust and prevents individual neurons from becoming too specialized. The key insight is that by training multiple subnetworks simultaneously, we create an ensemble effect that improves generalization. Let's start by importing the necessary libraries for our Dropout exploration. We're bringing in Pytorch and its neural network module, along with NumPy for numerical operations and Matplotlib with Seaborn for creating beautiful visualizations. I'm setting up a nice visual style for our plots, and importantly, setting random seeds for both Pytorch and NumPy to ensure our experiments are reproducible. This means you'll get the same results when you run this code. Now let's dive into the simplest example of using Dropout in Pytorch. Here's our first hands-on example with Dropout. I'm creating a Dropout layer with 50% probability, which means half of the neurons will be randomly dropped during training. We start with a simple 4x6 tensor filled with ones to clearly see what Dropout does. When we apply Dropout in training mode, notice how some values become 0 while others are scaled up to 2. This scaling is crucial. It preserves the expected value of the output. When we switch to evaluation mode using dropout.eval, the Dropout layer becomes an identity function, meaning it doesn't modify the input at all. This is exactly what we want during inference, consistent, deterministic predictions. Perfect, we can see the Dropout in action. In training mode, approximately half of our values are zeroed out, and the remaining values are doubled to maintain the expected sum. This scaling by 1 over 1 minus p is what keeps the layer's output statistically consistent between training and evaluation. In evaluation mode, as expected, we get back our original input unchanged. Let me show you another visualization of the Dropout process. This image illustrates the complete Dropout workflow, from the input tensor through the Dropout operation to the output. You can see how the Dropout mask is applied, randomly selecting which neurons to keep and which to drop. The scaling factor ensures that the expected value of the output remains consistent with the input, which is critical for maintaining signal strength through the network. Here's a comprehensive table documenting the two parameters of Dropout. The p parameter controls the probability of dropping an element, with higher values providing more regularization but also more zeros during training. The default is 0.5, which works well for most cases. The Inplace parameter determines whether to modify the input tensor directly or create a new one. While Inplace operations can save memory, they modify the original tensor, so use them carefully. Now let's explore how different Dropout probabilities affect our data. This is a comprehensive test of different Dropout probabilities. We're testing 5 different values from 0 to 1, using a large tensor of 1,000 elements to get statistically meaningful results. For each probability, we run the Dropout 100 times to calculate the actual drop rate and verify that the expected value is preserved. Notice how the scaling factor increases as p increases. When p equals 0.5, we scale by 2, and when p equals 0.8, we scale by 5. This aggressive scaling is necessary to maintain the signal strength. The results confirm that Dropout accurately implements the specified drop probability and successfully preserves the expected value through proper scaling. Excellent, our empirical tests confirm the theoretical behavior. The actual drop rates closely match the specified probabilities, and most importantly, the expected value of the output remains at 1 regardless of the dropout rate, except when p equals 1, which drops everything. This preservation of expected value is what makes dropout work so well in practice. Let's visualize these dropout probability effects with some nice plots. These visualizations really drive home the key points. On the left, we see that the actual drop rate perfectly matches our specified probability, confirming the implementation is correct. On the right, and this is crucial, we see that the expected value is preserved at 1 across all dropout probabilities. This is the magic of the scaling factor at work. Now, let's examine the Inplace parameter and understand when you might want to use it. Here we're comparing Inplace versus non-Inplace dropout operations. With the default non-Inplace operation, the input tensor remains unchanged and a new tensor is created for the output. They're different objects in memory. However, with Inplace equals true, the dropout operation modifies the input tensor directly and returns the same tensor object. This can save memory in large models, but be careful, you lose the original values. The key insight is that both produce the same dropout pattern, they just differ in memory usage and whether the original tensor is preserved. Perfect demonstration of the Inplace behavior. Non-Inplace operations preserve your original tensor, which is usually what you want for debugging and flexibility. Inplace operations save memory by modifying the tensor directly, useful when working with very large models where memory is constrained. Let's create a visual representation of dropout patterns to really see what's happening. Here's a beautiful visualization of dropout patterns across different probabilities. We're applying dropout to 20 by 20 grids to see the spatial patterns. This visualization really brings dropout to life. In training mode, you can see how increasing the dropout probability creates more sparse patterns, with more zeros appearing as black squares. The green squares show the scaled-up values. Notice how evaluation mode shows uniform green across all probabilities, confirming that dropout is completely disabled during evaluation. This is exactly the behavior we want. Now let's look at common pitfalls and best practices when using dropout. This image outlines the major mistakes developers make with dropout and how to avoid them. The most critical pitfall is forgetting to switch between training and evaluation modes, which can lead to non-deterministic inference results. Other common issues include using the same dropout rate everywhere, not understanding the scaling mechanism, and applying dropout incorrectly in the network architecture. Let's dive into the most critical pitfall, forgetting to switch modes. This example demonstrates why switching between training and evaluation modes is absolutely critical. I've created a simple neural network with dropout. When we run inference while still in training mode, even with torch.no_grad, we get different outputs every time because dropout is still randomly dropping neurons. This would be catastrophic in production. However, when we correctly switch to eval mode, we get identical, deterministic outputs every time. This is the number one mistake I see in production code. Always remember to call model.eval before inference. Perfect demonstration of the mode switching problem. Without eval mode, our model produces non-deterministic outputs during inference, which would be a disaster in production. With eval mode, we get the consistency we need. Always remember to switch modes appropriately. Now let's understand why the scaling factor in dropout is so important. This experiment clearly shows why scaling is essential in dropout. We're comparing proper dropout with scaling against a naive implementation without scaling. With correct scaling, the expected value of 2 is preserved regardless of the dropout rate. Without scaling, the signal degrades proportionally to the dropout rate. At 80% dropout without scaling, we lose 80% of our signal strength. This would completely break gradient flow and make training impossible. The scaling factor of 1/1 minus p is not just a nice to have. It's absolutely essential for dropout to work. The results speak for themselves. With proper scaling, our signal maintains its strength at 2 regardless of dropout rate. Without scaling, we see catastrophic signal degradation. At 80% dropout, the unscaled version reduces our signal to just 20% of its original strength. This would completely break deep networks. Let's visualize this scaling effect to really understand its importance. This graph perfectly illustrates why scaling is critical. The green line shows how proper scaling maintains the expected value regardless of dropout probability. The red dashed line shows the disaster that happens without scaling. The signal strength decreases linearly with dropout probability. By the time you reach high dropout rates, your signal is almost gone. This is why Pytorch and other frameworks automatically apply scaling in their dropout implementations. Now let's look at using different dropout rates in different parts of the network. Here's an improved network design that uses layer-specific dropout rates. We use a lighter 20% dropout on the input layer to preserve more of the original information. The hidden layers get standard 50% dropout for good regularization. Critically, we don't apply any dropout before the final output layer, as this would interfere with the model's ability to make precise predictions. This graduated approach to dropout is a best practice that balances regularization with information preservation at different depths of the network. Excellent, our network successfully implements layer-specific dropout rates. This design pattern is widely used in practice because it recognizes that different layers have different regularization needs. Input layers need to preserve more information, hidden layers benefit from stronger regularization, and output layers should maintain full precision. Let's examine how gradients flow through dropout layers during backpropagation. This experiment reveals how gradients flow through dropout during backpropagation. We create a tensor with gradient tracking enabled, apply dropout, and then backpropagate through a simple sum loss. The key insight is that gradients only flow through the neurons that weren't dropped. The gradient pattern exactly matches the dropout pattern. If a neuron was dropped in the forward pass, it receives 0 gradient in the backward pass. Additionally, the gradients that do flow are scaled by the same factor as the forward pass, maintaining consistency. This selective gradient flow is what makes dropout an effective regularizer. Perfect, we can see that gradients flow only through active neurons. About half of our elements have non-zero gradients, matching our 50% dropout rate. The gradient scaling of 2 matches our expected scaling factor, ensuring proper gradient magnitude during backpropagation. Let's visualize the gradient flow patterns through dropout. This visualization beautifully shows the complete dropout cycle. The input is uniform. The output shows the random dropout pattern with some values zeroed and others scaled up, and the gradient map shows that gradients flow only through the neurons that weren't dropped. This selective gradient flow forces the network to learn more robust features that don't rely on any single neuron. Now let's build a practical neural network that properly incorporates dropout. Here's a practical implementation of a neural network with proper dropout usage. The network uses increasing dropout rates deeper in the architecture, from 0.2 to 0.4, which is a common pattern. We apply dropout after the activation function, which is the standard practice. Notice there's no dropout on the output layer. The network correctly produces different outputs in training mode due to stochastic dropout, but identical outputs in evaluation mode. This is exactly the behavior we want for a production-ready model. Excellent, our practical network demonstrates proper dropout implementation. The architecture shows best practices with graduated dropout rates and correct placement after activations. The training versus evaluation behavior is exactly what we need: stochastic during training for regularization, deterministic during evaluation for consistent predictions. Let's explore an advanced technique called Monte Carlo Dropout for uncertainty estimation. Monte Carlo Dropout is a fascinating technique where we intentionally keep dropout active during inference and run multiple forward passes. By collecting these stochastic predictions, we can estimate both the mean prediction and the uncertainty. This is incredibly valuable for understanding when our model is confident versus uncertain. We run 100 forward passes with dropout enabled, then calculate the mean and standard deviation across these predictions. The standard deviation gives us a measure of epistemic uncertainty, how uncertain the model is due to limited training data. This technique is widely used in critical applications where knowing prediction confidence is essential. Great results from Monte Carlo Dropout. We can see that different output classes have different levels of uncertainty, with standard deviations ranging from about 0.044 to 0.06. This uncertainty information is invaluable for safety-critical applications where we need to know when the model is making uncertain predictions. Let's visualize the uncertainty estimates from Monte Carlo Dropout across multiple samples. This visualization shows how Monte Carlo Dropout provides uncertainty estimates for each class prediction across different input samples. Each sample has a unique uncertainty profile across the 10 classes, reflecting the model's varying confidence levels. This information is crucial for applications where we need to know not just what the model predicts, but how confident it is in those predictions. Let's wrap up with a comprehensive summary of best practices for using Dropout. The most critical takeaway is to always use model.eval for inference. This is by far the most common mistake. Understanding the scaling factor is essential. Dropout preserves expected values through automatic scaling. Use appropriate dropout rates for different layers, typically 0.1 to 0.2 for input layers, 0.3 to 0.5 for hidden layers, and potentially higher for deeper layers, but never apply dropout to the output layer. Monitor your validation performance carefully, as too much dropout can actually hurt learning. Remember that dropout works best with large datasets. The common mistakes to avoid include forgetting to switch between train and eval modes, using dropout during batch normalization, applying the same dropout rate everywhere, using dropout with very small datasets, and not understanding that dropout is only active during training. Use dropout when your model is overfitting, when you have sufficient training data, as part of a comprehensive regularization strategy, or for uncertainty estimation with Monte Carlo Dropout. Finally, there are advanced techniques to explore, including variational dropout for learning dropout rates, Monte Carlo Dropout for uncertainty estimation, spatial dropout for convolutional layers, and alpha dropout for SELU activations. With these best practices, you're ready to effectively use dropout in your deep learning projects.